today and tomorrow, we're going to talk about the same section. Today we're going to focus on increasing and decreasing intervals. Well, tomorrow we're going to focus on something called the first derivative test. Okay? But we need to know how to find increasing and decreasing intervals before we can do the first derivative test. Okay? Now, let's talk about increasing and decreasing. If we have a graph, one of three things can be happening. It could be increasing, which means our y values are rising. It could be decreasing, which means our y values are falling. Or it could be constant, which means our y values are staying the same. Okay? You know how to look at a graph to determine these things, but we need to be able to look at an equation and determine these things. And with calculus, we can do that. Okay, so let's talk about the calculus behind all of this, all right? If I have a graph that is increasing, it looks like this. What do we know about the derivative?
It's going to be on the positive side of the x-axis.
Okay, if we are increasing, then that means our derivative is positive, right? You can see that if we're increasing, all of those tangent lines would have positive slope. Okay, this is something that we work on in Unit 2. Do you agree? Okay. If we have an interval that is decreasing, what do we know about the derivative? It's less than 0. You can see in that picture. If we draw little bitty tangent lines, they would all have negative slope. Okay. If we have a decreasing function, we have a negative derivative. Okay? And the nice one, if it is constant, what do we know about the derivative? Okay? We have no slope there, which means our derivative is 0. We have 0 slope. Derivative is 0. Okay. So, just for practice, if I were to give you this graph right here, okay, what interval is f increasing on? From -3 to 1, f of x is increasing. Okay, where is this function constant? Oh, that's decreasing? Where is the function decreasing? Okay. You guys are fine, right? Okay. When you write increasing and decreasing or constant intervals, I would like you to use open intervals. Okay. I would appreciate that. Now, I'm going to give you an equation or a graph. And you need to be able to figure out where we have increasing and decreasing intervals. Okay, so today we'll just start with an equation. Okay, so here are your guidelines. First thing, you need to find critical points. Okay, as we did yesterday. okay? Our critical points are going to break up where we have relative minimums and maximums, okay? Potential relative minimums and maximums. And if we have relative minimums or maximums, okay, that's breaking up where we have increasing versus decreasing, okay? Now, we could have a critical point that's not a relative min or max, and that's okay, but we'll worry more about that tomorrow, okay? What I'm going to ask you to do is I'm going to ask you to draw a number line with those critical points. And what you're going to do is you're going to test values in between those critical points to determine if your derivative is positive or negative. Okay. I'll have you notate that by putting either a positive or a negative on that interval. Okay. So what's going to happen is it's going to look something like this. You're going to have a number line, you're going to put some critical points, and you're going to test to see what intervals are positive versus negative on the derivative. If our derivative is positive, we know we have an increasing interval. If our derivative is negative, we know we have a decreasing interval. So we can look at our number line and go from there. All right, ready? Okay. We'll start small. Okay. First of all, I need you to associate the words increasing and decreasing with derivative. Okay? If you see the words increasing or decreasing, we need to think about what's happening to the derivative. So we should find the derivative. Eli, what's our derivative?
We have squared ones.
That's a nice one, isn't it? Okay. Now, we need to determine where we have increasing and decreasing intervals. So we need to know where our potential relative minimums and maximums are, so we know how to break that up. So we need critical points. First of all, is this derivative ever going to be undefined? No, but it could be 0. So we're going to set this equal to 0 to find our critical points. So if we solve for x squared, we would get x squared is? So we have two critical points, positive and negative 2. Okay. So what I'd like you to do is make a number line. And do you see how I labeled it f prime? We're eventually going to have to do this with a second derivative, all right? To talk about something that you don't know about yet, but we're eventually going to have two number lines. So I want you to get in the habit of labeling, okay? Michaela, did you need to go? Okay. You just let me know when you're done. Okay. Keep going. Okay. So we're going to put our critical points on the number line. Okay, now this is our first derivative number line, which means when we are testing values in the interval, we need to test them in the first derivative. Okay, so I don't know, Between -2 and 2, what's a nice number to plug in? 0. You could plug in 1, but 0 I think would be easier. Okay? If we go to the first derivative and plug in 0, what kind of value would we get? We would get negative, specifically -12, but I don't even care about -12. I care about negative. So I'm going to make a little negative sign because between -2 and 2, our derivative will be negative, no matter what you pick. You can pick 1, you can pick 1.5, you can pick 1/2. But we don't want to pick those numbers, right? Okay, how about below -2? What do you want to pick? -3, why not? So we have 3 times -3 squared would give us 27 minus 12. I don't care what that number is, but I do care that it is positive. Okay? And if we picked a number in this interval, like, I don't know, +3, okay? 3 times +3 squared minus 12 will also give us a positive number. Okay? Those are calculations that you can do in your head, right? I don't need to see work for that. But I do need to see your number line with those positive and negative signs. Okay? So this is what happens. We are increasing on any interval where our derivative is positive. So our derivative is positive from -infinity until -2 and from 2 to infinity. Our function is decreasing anytime our derivative is negative. Well, our derivative is negative on the interval -2 to 2, so our function is decreasing on the interval -2 to 2. And that's it. Now, obviously, we're going to do some more examples, but right now, are there any questions on the process that we just took? Okay. Same process as yesterday as far as finding critical numbers. We're just doing something different with them. Next one. Okay. We need to find where our function is increasing and decreasing. What word should trigger in your brain when you see increasing and or decreasing? Derivative, specifically the first derivative, because we will work with the second derivative later. Okay, so first derivative, let's find it. First derivative, Eric, how do we do that? That's what we can talk through it.
Okay, so we do the power rule and you have 2/3 times the quantity x squared minus 9 to the power of -1/3 minus 2.
Do you agree?
Yes.
Good, because it's right. All right. Now, before, we could leave it like this, right? But now that we have to determine critical numbers, we should probably rewrite this to look nicer. Okay? And we should probably not leave negative exponents. Okay? So we can write this as 4x over 3 times x squared minus 9 to the positive 1/3. How do you feel about that? Okay. To determine critical values, critical numbers, or whatever you want to say, Okay, we need to determine where the derivative is 0 and undefined. Now, you don't always have to show me this work. In a problem like this, sometimes it's a little more obvious, right? Where is our derivative 0? Okay, so our derivative is 0 when the numerator is 0, 4x is 0 when x is 0. Okay, what about undefined? Our derivative is undefined when the denominator is 0. Which is where? How about plus or minus 3? All right. Okay. Now we should probably, sometimes we may have to think about the domain, right? If this was like a square root, we'd have to be a little bit more careful about the domain. But since it's technically a cubed root, we can have positive and negative numbers. We don't have to be super concerned about it. Okay. All right. So now, on our derivative number line, we have 3 critical values. We have a critical value of -3, +3, and 0. Okay? Now, I don't think that this is something that requires a calculator. We just basically have to decide what kind of number we're going to have, positive or negative. Okay? So, let's start with... Oh, that's sad. Are they going to come back? I don't know. Okay. Let's go to this interval right here. What number would you like to pick? -4? Okay. -4 would make our numerator negative. Do you agree? And our denominator would be what kind of number?
Positive.
Positive, because we'd have 16 minus 9 right there. I don't care what the number is, but we know we have negative over positive. All right. Between -3 and 0? -1. Sure. Okay. -1 would make our numerator -4, but it would make our denominator negative, right? We'd have -8 to the 1/3 power, which we could figure out, but we don't have to. We know we're going to have a negative divided by a negative, so we have a positive derivative right there, which means that entire interval will be positive for our derivative. Do you remember doing something similar to this in pre-calculus?
Yeah.
Kind of. I mean, it was for inequalities, but... 0 and 3, we could plug in 1, or 2, or 2.5, but I wouldn't. 1's nice. We would get a positive number upstairs, but then 1 squared minus 9, that would be negative. So we get we get a positive divided by a negative. Okay. And then if we go to the very right interval, we could plug in 4. That would make our numerator positive and our denominator positive because we'd have 16 minus 9. And so we'd have a positive derivative there. All right, so if I ask you for increasing or decreasing intervals, this function is increasing where our derivative is positive, which turns out to be between -3 and 0 and 3 to infinity. We are decreasing on any intervals where our derivative is negative. So from -infinity to -3 and 0. I like this week in calculus, okay? We had actually, first of all, do something with our derivative, but each day we're just adding like one more little piece. So tomorrow we'll talk about when it switches from increasing to decreasing and decreasing to increasing, those types of things. So kind of keep that in the back of your head for tomorrow. But we actually get to find the derivative and do something with it instead of just find it, okay? I like that. Okay, now I do want to talk about the case when we would have like f of x is x cubed. We all know what that graph looks like, right? Think about that graph in your head. Okay. What's its derivative? Okay. So when is the derivative 0? At 0. Now, what happens though? If we plug in negative numbers, what's true about our derivative? If we plug in positive numbers, our derivative is positive, okay? We know in our head that this function doesn't decrease, right? But you are not going to tell me that it increases from negative infinity to infinity. This function would be increasing from negative infinity to 0 and then 0 to infinity. It's technically not increasing at 0, which is something that we never really talked about last year in pre-calculus because you don't really know about the concept of a derivative. But since the derivative is 0 at 0, it's actually breaking up that function into 2 increasing intervals. Okay. All right. This is the last example. That is an x to the 4th. Okay, my projector looks like it's off by like. What I'd like you to do is take the next, let's say, 2 minutes, and as a pod, find that derivative nice and simplified. Okay. You can talk louder to each other, by the way, don't whisper.
I got 4x and then minus 2x to the 5th. Or I guess it's, yeah. So I got 2x to the 5th plus 2x over. Oh, yeah, that's right. Minus 4. Yeah. Yeah. So 2x to the 5th minus 2x over x to the 4th. Yeah.
And then you guys see 2x to the 4th minus 2 over x cubed.
So,
All right, Henry.
Yeah.
What do you got?
I messed up.
You're redoing it. Okay. Where are you in your work? Okay. So what do you get? You get 2x to the what?
2x to the 5th minus 2x all over x to the 4th.
Never go like just 0 because.
Okay, x to the 4th like that?
Yep.
Okay, this is what Henry got. Do you agree? Okay.
Wait. Can you like take an x out of all of them though?
Answer this question for me.
Yeah.
Yes. You can factor an x out of the numerator, cancel it with 1 in the denominator to be 2x to the 4th minus 2 over x cubed. Is that helpful?
Yes.
It is helpful. You do want to simplify if you can. All right, we're to the point where simplifying is going to help us in the long run, okay? So it would be a good idea to do that. Okay, now we need to determine what our critical values are. So we need to determine where the derivative is 0 and undefined. Okay, we'll start easy. Where is our derivative undefined? Yay, 0. Okay, now let's talk about where it's 0. Some of us may need to do some algebra. Some of us may want to do this in our head. I'm going to tell you right now, I really don't have a preference, okay? I know that some of us can do some calculations in our head, and the algebra isn't what I'm the most concerned about right now. So, if we set the numerator equal to 0, we get 2x to the 4th equals 2, which means x to the 4th equals 1. Be careful.
Plus minus.
X is plus or minus 1. Anytime we do an even root to both sides, we have to have the plus or minus. Okay? Now, this is going to be like the one situation where we do have to work with fractions. It's going to be okay. Please trust me. All right. So let's start with the non-fraction computations, all right? What would you like to plug into the right of 1?
2.
10 would be fine. 2 would also be fine. I think that would think, you know what? It doesn't matter. Let's do 10. What the heck? 2 times 10 to the 4th, is it going to be bigger than 2? It is, which means our numerator is going to be positive. 10 cubed is also positive, so we would have a positive fraction. Okay, to the left of -1, if you wanted to be obnoxious and choose -10 to plug in, okay, is 2 times -10 to the 4th minus 2 going to be positive? Yes. What about -10 cubed? It would be negative, so we would have positive divided by a negative, we'd have a negative number. Now, if you need to make some chicken scratch calculations to the right of your, go for it, all right? But you can do this in your head if you'd like. Okay, between 0 and 1. 1/2. Did you have a question? Okay, just give me like 2 minutes. Let's get to the end of the video, okay? All right, 1/2. 1/2 to the 4th would be 1/16.
Yes.
Times 2 would be
1/8.
1/8. Minus 2 would be a negative number. Divided by 1/2 cubed, that would be positive. Okay, now here's what's nice. We can choose -1/2, and the calculations are going to be similar. We would still have a negative numerator, right? But then -1/2 cubed would be negative. Negative divided by a negative would be positive. Yes.
You can see a pattern of negative and positive.
No, you can see a pattern,
Sometimes.
but that's not always going to happen. Like in the case of that cubic function, right? Okay, you could have a function do something like that where it's increasing, increasing, decreasing. So don't get too caught up in patterns, okay? As far as like the plus minus. Yes, I know we've seen that, and more times than not you will see that, but don't get too caught up into it. All right, so we are increasing from -1 to 0 and 1 to infinity because that's where our derivative is positive. And we are decreasing from -infinity to -1 and 0 to 1 because that's where our derivative is. All right. What do you think?
It's easy.
Well,
Easy way.
have some confidence. I like that.
Easy.
Let me go ahead and stop.